everyone, it's Miss H, and this is going to be our final video on electricity and magnetism. So this is our final video for this unit. This time we're going to be looking at the last little bit of electricity as well as the relationship between electricity and magnetism itself. So a transistor is an electrical component that uses a small electric current to produce a large one by one of two methods. So a transistor is a way of amplifying a current or a way of making an electrical current bigger than what it normally would be. So the first is an amplifier. So a small electric current goes into the transistor and it amplifies the signal to make it into a larger one. So in this case, it's the same signal going in and coming out. It's just larger or stronger when it comes out than when it went in. The other way is a switch. So with the switch, a small electric current goes into the transistor and trips the switch, which causes a larger current to flow out in another part of the circuit. So in this case, technically it's a different signal. It's coming out as a larger signal somewhere else instead of the same small signal going in and being made bigger. That small signal triggers the release of a bigger signal somewhere else. You probably have heard of transistor radios. Those are kind of an older type of radio that used the amplifier method. The next thing is a transformer. Now this is not the movie franchise, obviously. This is that big metal box you see outside of a house that has all those warnings of it, do not touch, all that kind of thing. So transformers are devices that can decrease or increase the voltage. This only works with alternating current. So the ones that we see in the big boxes outside of homes and businesses, that sort of thing, those are trying to decrease the voltage. And other devices, like handheld devices, that sort of things, you might see a transformer that will increase the voltage because you're trying to make the signal or trying to make the voltage stronger in order to make it work better. Okay, so a step-down transformer reduces the voltage. So with the step-down transformer, you have more turns on the primary coil than the secondary coil, and I'll show you a picture of that in just a second. So what happens is that the incoming is bigger than what's going on the outgoing. In the step-up transformer, you increase the voltage, so there are more turns of wire on the secondary coil than there are on the primary. And again, this is much easier to understand with the picture, which I'll show you in just a second. But with the with the secondary coil being bigger than the primary, that means that it's bigger going out than it was coming in. You can almost think of it like a funnel or reverse funnel versus a funnel. So here are two pictures of our step-up and step-down transformers. So you can see on the top is the step-down transformer. So the input voltage is on the left, and so that's a much bigger signal than what comes out on the right. And that's again because you have an iron core with these coils wrapped around it, and as the electricity flows through and that goes through the smaller turns of coils, that causes the voltage to decrease. On the bottom with the step up, again, everything's set up the same except that your primary and secondary coils, now your primary is smaller than your secondary, so that makes the output bigger than the input was. So now I'm going to look at magnetism. So a magnet is a piece of metal that applies a force to other metals in electrical currents, causing attraction or repulsion. So magnets always contain either iron, nickel, cobalt, or some combination of the three. Those are the three metals that are naturally magnetic. Now we do have magnets that we've made since then that allow us to have magnets that do not contain one of those metals. There are also some other ones, some of the rare earth metals that can be made magnetic naturally as well. But these are the three that are in any kind of common magnets are going to be iron, nickel, or cobalt. The Earth's core is iron and nickel, and that's what allows it to be magnetic. Excuse me, the opposite ends of the magnet, the north and south pole, will attract each other, while the like ends of the magnet, either two north poles or two south poles, will repel each other. So if you've ever tried bringing two magnets together and they seem to push apart, that is because they are both the same pole. They're both north or both south. If you try to bring two magnets together and they just want to snap together right away, that is the opposite ends of the magnet, one north pole, one south pole. A magnetic domain is a field where the atoms are grouped together and aligned with one another. You can almost think of it as like a miniature magnet within the material. So basically all of the magnetic magnetism lines up. Without all of the magnetic domains lining up together, you don't have a magnetic material, because we know that not all iron, nickel, and cobalt is a magnet. In order to turn that piece of iron into a magnet, you have to get all of those magnetic domains aligned. So normally there's a domain here and a domain there and a domain here and a domain there, and they're all of them within that domain are going one direction, but the domains themselves might all be going different directions. And so in order to be magnetic, the domains all have to be lined up going the same direction. So magnets come in one of two types, permanent or temporary. So permanent magnets hold their magnetic properties for a long time. We're talking about years, decades, centuries, millennia. Temporary magnets hold their magnetic properties for a very short period of time. We're talking about as short as seconds or as long as a few years, maybe a couple of decades, but not longer than that. They are typically produced by being brought near a permanent magnet or are induced with an electric current. So for example, if you have, say, a paper clip that has been attached to a magnet for a while, when you first take that paper clip off of the magnet, it itself will be magnetic and will be able to pick up a couple paper clips, but that magnetism only lasts for a few minutes usually, not any longer than that. We can also create a magnet with an electrical current, which is what we're going to talk about on the next slide. Okay, if you break a bar magnet in half, it results in two smaller magnets that each have their own north and south pole. If you break any magnet, it's still going to have a north pole and a south pole. It is, as of right now, it is impossible to create monopoles, which is having just one pole or the other. So when you break a magnet, typically it's still going to be a magnet. It's just going to be a smaller version than what it was. It is possible that when you break the magnet, you could also do something else to disrupt its magnetic properties, so that would make it so just no longer a magnet. But typically speaking, breaking a bar magnet results in two smaller magnets that each have their own north and south pole. So electromagnets, as the name implies, are temporary magnets formed by passing an electrical current through a wire wrapped around a metal core. So because you have you're taking wire, and you can actually do this yourself at home, take a wire, preferably one that's insulated, because if it's not, the magnetism is going to kind of escape and not be where you want it to be. You can wrap it around a nail and then attach each end of the wire, strip the ends of the wire, attach each end to a battery, and it will actually create a small electrical field. Just make sure you don't leave it there too long, because if you do, it does start to heat up because there's not a whole lot of resistance there. And so you're going to end up getting burned, and we don't want you to do that. So how can you increase the strength of your electromagnet? You can increase the number of turns of wire. So the more times you wrap the wire around the nail, the stronger the electromagnet becomes. You can increase the voltage of the battery or the power source that you're using. Again, if you're going to try this at home, I recommend just using a standard little 1.5 volt AA, AAA C or D battery, not anything bigger than that. A 9 volt battery would lead to burning a lot faster, and you don't want that to happen. Okay, and you can also increase the size of the core, so using a little tiny skinny nail versus a big fat nail, or using a nail versus a piece of solid metal like rebar. Another term that you'll sometimes see is solenoid, and a solenoid is an electrical coil of wire with a movable core at the center. So the big difference between an electromagnet and a solenoid is that, first of all, the purposes and what they do. So they actually do two different things in terms of where we use them and apply them. But a solenoid has a movable core, and an electromagnet doesn't typically. So going back to the electromagnets, also that's really our transformers, are essentially versions of electromagnets where you have those coils wrapped around the iron core. So that pretty much sums up everything else we needed to know about electricity and magnetism.